In the first two sections of Chapter 15, the most important idea by far is this one right here. Whenever we talk about a wave, the speed at which that wave travels depends only on the characteristics of the medium that the wave is passing through. For example, as you read in the first couple sections of Chapter 15, the speed of a sound wave depends on the temperature of the air or whatever gas the wave is traveling through. It depends on how heavy the molecules of that gas are. And another example that you saw there in the first couple sections of Chapter 2 is that for a string or any other thing that could be modeled as kind of like a string, for instance, the vocal folds at the back of your throat that produce the sounds of your voice, the speed of waves on a string or on any string-like system depends on just two factors. The tension in that string, and then this factor called mu, lowercase Greek letter mu, which is really a ratio of the total mass of the string to the total length of the string. Mu is a measure of how thick or how dense that string is, how many kilograms per cubic meter on that string, or how many grams per centimeter. Well, let's imagine some of the calculations, some of the things that we could do thinking about this particular relationship. Imagine one string, a guitar string or a piano string, and you tune it to the correct pitch by adjusting the tension in the string. Now, obviously here we see that adjusting the tension changes the speed, and later on we'll see how the speed is connected to the pitch of that string. But it's the same string all the time. We're adjusting only the tension. So tension is a variable. Mu is a constant factor. So we can rewrite this equation in this way, where some variable, speed, equals some constant, 1 over square root of the constant mu factor, times another variable, square root of tension. That's the form for direct proportionality. Some variable equals some constant factors times some other variable, and one must be careful in this case. Remember that this equation is telling you that everything in this term that isn't a constant factor is the variable. And everything here in this term that isn't the constant factor, here's the constant factor inside the parentheses, everything that isn't the constant factor isn't t, it's square root of t. So the proportionality we have here is speed is directly proportional to square root of t. The relevant variables here are speed and square root of t. We're all used to thinking of a symbol like t as representing a variable, but if t is a variable, then square root of t is just another equally valid name for some other variable. And remember what direct proportionality means. It means that if one variable changes by some factor, the other variable will change by exactly the same factor. So let's say speed changes by some factor. The new speed is just some number times the old speed. Then the other variable, square root of t, changes by exactly the same factor. If this is the case, then whatever thing that v is proportional to, we can just substitute the new and the old values into this same pattern, this same equation, and we have something that's equally true. Instead of the new v, we have the new thing that v is proportional to, square root of t. And instead of V1, we have the old thing that V is proportional to. Old, original, first square root of t. So let's look at a specific example here. Let's say we have a string, and on that string, the speed of a wave traveling on that string is 100 centimeters per second. And now let's say we tighten the string, we increase the tension, and we increase it quite a bit, so that the new tension is 3/2, 50% larger than the old tension. We don't know what the old tension was. We don't know the numerical value of the new tension. We don't have to when we're thinking about proportionalities here. Well, the proportional relationship is between speed and square root of t, not between speed and t. We have to know how t square root of t changes, and that'll tell us how speed changes. But of course, from this, we can figure out how square root of t changes. Just take the square root of the whole equation, and we'll have our answer to that question. Square root of the left-hand side must equal square root of the right-hand side. So the variable called square root of t, here's the old value of that variable called square root of t. Here's the new value, and the new value of square root of t is this factor larger than the old value. So speed change, this is the factor by which square root of t changed. So velocity being proportional to that changes by the same factor. The new speed is square root of 3/2 times the old speed, which was 100 centimeters per second. Square root of 3/2, ask your calculator to tell you what that is, about 1.22. So the final result is that this is about 1.22, this is 100, so the new speed is about 122 centimeters per second. Now let's take a look at the same relationship between speed and square root of t, but we'll go the other way. In this case, we will start by knowing how the speed changes, and from that deduce how the tension changed. In this case, we knew how the tension changed and deduced how the speed changed. So in this case, let's say we start out with a string that has a tension of 400 newtons, and in that case, that produces some particular kind of speed along the string length. Now we tighten up the string, but we don't know by how much. What we do know is that by tightening up the string, increasing the tension, we've increased the speed. And in this case, we have increased the speed by 10%. The new speed is 1.1 times the old speed. The new speed is 10% greater than the original speed. So, go back to proportionality. We know how speed changes, so we know the factor by which speed changes, so we know the factor by which anything proportional to the speed changes. That means we know the factor by which this thing, which is proportional to the speed, how this thing changes. In other words, the new value of this thing, the new square root of t, changes by the same factor, 1.1, times the old value of this thing, square root of t1. We know what t1 is. We're trying to solve for t2. We can solve for t2 by just getting rid of that radical sign. You get rid of the radical sign by squaring everything. So square of the left-hand side, just plain T2, equals square of the right-hand side, which is 1.1 squared, times square root of T1 squared, or T1. T1 was 400 newtons, so T2 will now be about 484 newtons. Speed increased 10%, but because the relationship is between speed and square root of t, not between speed and t, we had to increase the tension by more than 10%, about 20%, to in order to get the speed to increase by 10%. One more example. Let's look at the relationship between speed of the waves on that string and mass of the string. So our basic relationship, remember, speed is square root of tension over that mu factor. Mu is just mass per unit length. Let's say we get a much thicker string, a string where that has a mass 50% larger than the old mass. Same length of string, but just now a much thicker and therefore more massive string. And so the value of mu will now be 3/2 times the old value of mu. Okay, now we're assuming in this case that when we replace the first string with the thicker, heavier string, we're going to keep the tension the same. So constant tension and we vary mu. So let's rewrite our basic relationship here in the proportionality style. Speed is just a constant factor, which is square root of tension, divided by some variable, square root of mu. And that equation is in the pattern for inverse proportionality. It's just some variable, speed in this case, equals a constant factor, square root of tension, divided by some other variable, which in this case is square root of mu. Inverse proportionality. The speed is proportional to the inverse of mu, or inversely proportional to mu, however you want to say it. And remember what inverse proportionality means. Whenever one variable changes by some factor, the other variable changes by not the same factor, but the inverse of that factor. So, for example, if the new value of square root of mu is just some factor that I'm calling n times the old value of that variable, the old value of the square root of mu, then speed will change by the inverse of that factor, 1 over n. That is, the new speed will be 1 over n times the old speed. And let's see how that works. Let's assume a situation where with the original string, the thinner, lighter, less massive string, the speed was 100 centimeters per second. And now, as I said before, increase the mass and therefore increase mu by a factor of 3/2, increase it by 50%. So the new mu is 3/2 times the old mu, but the change in mu is not what's related to the change in speed. The change in the square root of mu, that's related to the change in the speed, because those two things are proportional. Keep that there, don't want to erase it. So I need to know how square root of mu changes, and I can get that from this equation just by taking the square root of everything. Square root of the left-hand side equals square root of the right-hand side. So the square root of mu changes by a factor of square root of 3/2. So speed will change by the inverse factor, the inverse of that factor. So the new speed is the inverse of this. That'll be the square root of 2/3 times the old speed, which was 100 centimeters per second. So now speed is now going to be smaller than it was before, and that'll come out to about 82 centimeters per second. So more proportional situations. We've seen many of them. We'll see many more.